Okay, students, Assalamu alaikum. Right now I'm sharing with you the screen for chapter number 2. Can you see this on your screen?
Jesus.
Okay. So last week we started the first law of thermodynamics. Okay. Anybody want to say anything? Okay. So last time we started first law of thermodynamics. I explained you about that a bit, that it is basically conservation of energy principle, which talks about the total amount of energy going in and out of the boundaries through of the system is responsible for whatever the changes occurring within the system. We discussed about that, and we developed the basic equation, which will be the fundamental equation for the first law of thermodynamics. And we talked about it, that the basic equation for this will be this is so we talked about it, that this is the fundamental equation for the first law of thermodynamics, where we where we defined Q as basically the net heat input. So we defined Q as equals to Q in Q, Q in minus Q out. This was how we defined Q. At the same time, we said that W is the net work output. So we define W as W equals to W out minus W in. So this was basically W. So we have net heat in minus net work out is plus total energy of the mass going in minus total energy of the mass going out through the boundary. So this is all what is happening on the boundary. This thing is equals to whatever is the change occurring within the system itself. So it could be the change in the kinetic energy, it could be change in the potential energy, or it could be the change in the internal energy of the system. So this was the first law of thermodynamics equation, the main equation which we developed last time for in the course of thermodynamics. So before moving forward, I need to know, is there anything which is not clear to anybody in the development of this equation of the first law of thermodynamics? You can ask.
Yes, sir.
Okay. Because this is the fundamental equation which is now going to be behaving as the main starting point for analyzing different thermodynamic systems for in the subsequent chapters. So we are in chapter number 2 in this course, and we are developing this equation, and after that we are going to apply these equations to different systems, and like for example closed systems, open systems, in chapter number 4 and 5 in the next weeks. So okay, if anybody want to ask anything so far, you can ask. Okay, let's say when we apply this equation, the first law of thermodynamic equation, to closed systems. Okay, so when we say it is a closed system, so how do we define closed system? Closed system is a kind of a system where mass cannot go in and out of the boundary. If mass cannot go in and out of the boundary, this means what? It means E mass in and E mass out will be zero. Okay, so since mass cannot go in and out of the boundary, so E mass in, E mass out will be zero. So for closed systems, the first law of thermodynamic equation will be simplified to this Q minus W will be equals to delta kinetic energy plus delta potential energy plus delta U. Is it clear?
Sir, delta is the total internal energy.
Delta U is the change in the internal energy. We are saying is that whatever is happening at the boundaries of the system is responsible for whatever the change occurring within the system. So this is what's happening at the boundary. Heat is going in and out, or work is going in and out. Work is being done on the system or by the system. Okay, so this is what's happening at the boundary. So this is going to change what is happening inside the system. So inside the system, it has its kinetic energy. It might change. Inside the system, it has its potential energy that might change. Inside the system, it has its internal energy that might change. So when we say delta U, delta kinetic energy, delta potential energy, so these are the changes of different forms of energy inside the system, which is happening because of what's happening at the boundaries. Is it clear?
जी सर.
The one who asked the question, is it clear to you?
Yes, sir.
Okay. Now, as I told you, we have also, like, for example, adiabatic systems. So adiabatic systems are the kind of systems where heat cannot go in and out of the boundary. So if I say that the system is adiabatic, so which term will be zero?
Sir, work done.
No, it will be Q. Because I'm saying Q is the heat transfer. Okay, so if I'm saying that it's adiabatic and heat cannot go in and out of the system, then Q will be zero, right? And suppose if I say that the system is stationary. Stationary means the system is not moving, so that means kinetic energy will be zero. And if the system is not moving, so change in potential energy will also be zero. I'm not saying the potential will be zero, but I'm saying change in potential energy will also be zero because the system is not moving. So initial potential energy will be the same as the final potential energy, so change in the potential energy will also be zero. Is this point clear?
Yes, sir.
Okay, so expect one different kind of question in the exam, that I provide you this first law of thermodynamics equation, and I ask you to, let's say, simplify this equation for closed and adiabatic system, or let's say for adiabatic and a stationary system. Okay, or let's say for closed and stationary system. So by the specific definition of the system, you can actually simplify this equation. Okay, so if it is said adiabatic, that means Q will be zero. If it is said closed, that means E mass in, E mass out will be zero. If it is said stationary, that means delta kinetic energy, delta potential energy will be zero. Okay, so this is the main fundamental equation which you can simplify it to whatever and apply it to whatever the system we have. Okay, so based upon the definition of the system, okay, you can actually simplify this first law of thermodynamics for that system. Is this point clear?
Yes, sir.
Okay. We can write these energies in on the rate format as well. Like, for example, now then it will be in kilowatts per unit time, or on the unit mass basis as well. Then it will be kilojoule per kg. So, okay, let's talk about a special case for a closed system undergoing a cycle. The initial and okay, when we say thermodynamic cycle, so cycle means whatever the initial state will be, whatever the final state, it will be the same as the initial state, because a cycle means it starts at one point and then after following through multiple process, it ends up at the same point. So if I say what is the initial and what is the final, it's the same point. So initial and final same point means all the initial energy and all the final energy will be the same. So when we talk about the first law of thermodynamics, so in first law of thermodynamics, we are dealing with the change in the energy from initial to final, okay, here. So if we are talking about a thermodynamic cycle, so for a cycle, this delta will be zero because the initial and final state are the same, right? So for the case of a thermodynamic cycle, okay, first of all, delta E will be zero. Okay, so when delta E will be zero, that means all these energies, summation of them will be zero. So we'll end up with Q minus W plus E mass in minus E mass out. Okay, suppose if it is a closed system, then for a closed system, E mass in and E mass out are also zero. So let's say we talk about a closed cycle. So delta U, delta kinetic energy, delta potential energy, total delta E will be zero. E mass in, E mass out will also be zero because it's closed. So what we are going to end up with, Q minus W equals to zero, or we can say that Q is equals to W. So this would be the format of the equation for a specific case if it is if it is a cyclic process and it is a closed system. Is this point clear?
So can you repeat this thing again?
Okay. Well, what I'm saying is that whenever it is a cycle, that means it starts from a specific state point, and this after going through multiple processes, it ends up at the same state point, because this is a cycle. Starts from something, ends up at the same, and ends up at the same state as the starting state. Okay, so whenever we talk about cycle, that means the overall change in the energy will be zero because the start and end point is the same. Is this concept clear to you or not?
Yes, sir. It is a ideal case.
You can say not necessarily ideal case. Okay, we're going to discuss about this. There is a specific level of ideality inside it as well. However, it will follow still the second law of thermodynamics. So when we come to that, you're going to understand it much better. But right now, just understand the concept of cycle and how a thermodynamic cycle, when we apply the first law of thermodynamics over thermodynamic cycle, how the equation will be simplified. So at this point, just understand till here. When we talk about the thermodynamic cycle, that means the change in energy from initial to final state will be zero. So delta U, delta kinetic energy, delta potential energy together will be zero. Okay, so overall change in energy will be zero. That means what? That means if it is a closed system, then E mass in, E mass out is also zero, and we are going to end up with Q minus W is equals to zero, which means Q is equals to W. So whatever the heat we are going to supply will end up producing work out, or whatever the work out, whatever the work in will be equal to the amount of heat added into the system. So is this point clear?
Yes, sir.
Okay.
जी sir.
Okay, so let's have a numerical here, and let's apply the first law of thermodynamics for a specific case. Okay, so first of all, we say this is a rigid tank. Remember, in thermodynamics, whenever there is a specific numerical equation, the wordings of the numerical are very important, because many times a specific word means specific scientific thing. Okay, so for example, when it said rigid here, so rigid means what? Rigid means it's not deformable, something which is not deformable, something which is going to retain its shape, which is going to retain its size. So what we mean to say is that the volume change will be zero. That means we are saying that delta V is zero. Okay. Anyways, for this question, this point does not have any specific significance. However, I want you to understand this thing, that whenever we say rigid means change in volume will be zero. This is a specific thing, and this is a specific terminology. You're going to face this terminology in chapter number 3. And there, this word will have a specific meaning and will have a huge significance in the solution of the problem. Okay, so the point to give you the understanding is that whenever it is written rigid, so something should come in your mind, and that is the change in volume is zero, because the volume is not going to change because it is rigid. It is not deformable. Its volume and shape and size would remain the same. Do you understand the word rigid here?
Yes, sir.
Okay.
Yes, sir.
Okay, we have a rigid tank that contains a hot fluid that is cooled while being stirred by a pedal wheel. Okay, so we have this is our tank. Okay, this tank is inside the tank we have a fluid. It's a hot fluid. Okay, and there is a pedal wheel. Okay, and obviously the shaft of the wheel is going to rotate. So there will be rotation of the wheel. Okay, so basically work is being put from outside to in. So this is work in. Okay, so we have a specific pedal wheel here. Okay, uh, okay, so this fluid is being cooled. Said is that the hot fluid that is cooled. When it says that is cooled, so that means some of the heat is going out. Okay, while being stirred by a pedal wheel. So work in is there, and there is some heat out, going out because it is cooled. Okay, so some heat is going out of this tank. Initially, the internal energy of the fluid is 800 kilojoule. So what do we have here? Initially, U, because we are talking about internal energy. Okay, so we are talking about internal energy. That means U, and we are saying initially. So that means U1 is given. Okay, so it's 800. Okay, during the cooling process, the fluid loses 500 kilojoule of heat. So how much is the amount of heat going out? What is the amount of Q out? That's 500 kilojoule. Okay, and the pedal wheel does 100 kilojoule of work on the fluid. So 100 kilojoule of the work is done on the fluid by the pedal wheel. So this is 100 kilojoule. Okay. Determine the final internal energy. Final. That means we need to find U2. Determine the final internal energy of the fluid. Neglect the energy stored in the pedal wheel. Okay. So we need to find what will be the final internal energy of the fluid. Before moving towards the solution of the problem, first of all, do you understand the problem statement or not? We have a tank. Inside the tank, we have a fluid. The fluid is hot. Heat is being going out of the tank, and some work is being done on the fluid by the pedal wheel. We need to know that what will be the final energy of the fluid. Do you understand the problem statement? Is there anything within the problem statement which is not clear to anybody?
Yeah, it's understood.
Okay. Now, since we need to find U2, okay, so let's apply the first law of thermodynamics here, okay? So first law of thermodynamics is basically what? Says Q minus W. Okay, first of all, this is a rigid tank. There's no mention of any mass going in and out. There is no mention of mass going in and out, so I'm just ignoring the mass term, okay? So the Q minus W plus E mass in minus E mass out, but E mass in, E mass out will be 0 here, will be equals to delta U, okay, and delta kinetic energy, delta potential energy. There is nothing mentioned about the motion of this tank. The tank itself seems that it is stationary. So we are going to assume it that way. If we assume the tank is stationary, then delta kinetic energy, delta potential energy will be 0. So our first law of thermodynamics for this case is going to end up like this. Do you understand how we simplify the first law of thermodynamics for this specific case?
Yes, sir.
Okay. Now Q minus W will be equals to U2 minus U1. Okay, so we need to find U2. We already know U1. Okay, Q is Q in minus Q out, but Q in is not mentioned here anything, so Q in will be 0. It's just Q out here. Okay, So Q will be equals to 0 minus Q out, because Q is Q in minus Q out. Okay, so Q is Q in minus Q out. Okay, Q in is 0, Q out is mentioned. This is 500 kilojoule is Q out. So Q will be what? It will be minus 500. Okay, so that will be minus 500. And what will be W? W will be W out minus W in. W out minus W in. Is there any mention of any work being done by the fluid outside? So there is only work which is being done on the fluid, but there is no work done by the fluid on the surrounding. So basically W out will be 0 here, but W in is mentioned. It's 100 kilojoule. This is W in. So W will be what? It will be minus 100. So minus 100 you're going to put here. Minus minus will become positive. So it will become what? Minus 500 plus 100. Is this point clear or not?
Yes, sir.
So it will become minus 400, which will be equals to U2 minus U1. And U1 is 800, so you can find what is U2. So you can see the solution. So it will be minus 400 equals to U2 minus U1, which so U2 will come out to be, so U2 will come out to be 400 kilojoule. So we have solved this problem. Is the solution here clear or not? Is there anything within the solution which is not clear? Please ask. You have to understand one thing, that you need to memorize the definition of Q and W. You see here, from the definition of Q, I just place the values of Q in and Q out into it, and I get the value of Q, whether it is positive or negative. Similarly for W, W definition is W out minus W in. I just place the value of W in, W out from the given, and I'll get the value of W, whether positive or negative. Then once I have the values of Q and W, whether positive or negative, I'm going to put it into the main first law of thermodynamics. And there is a negative sign here within the formula of first law of thermodynamics. So here it becomes positive 100 because W was negative 100. And then this negative multiplied by the negative within the formula of first law of thermodynamics becomes positive 100. Okay. So if you just, sorry.
सर फ्लूइड कंटेनर पे कोई अपना वेट एक्सर्ट नहीं कर रहा
Container ka weight, but container ka weight is not going to affect the fluid because the fluid is inside the container.
इसका वेट कंटेनर को इफेक्ट नहीं कर रहा मतलब वो वर्क डन नहीं कहलाएगा
No. Work done, for work done, there has to be some motion. Okay, the container is stationary and the fluid is stationary. So yeah, there is the weight of the container, but the weight is not doing any work because it's not moving. You need to have some distance covered, right?
ओके जी
Okay. For the case of the shaft, there is a circular motion. There is a rotational motion. So the motion is there. There is a torque. Okay, so that's why there is work in. Okay, but for the case of container, yeah, the weight is there, but the weight is not making the container move. So there is no motion. The container is like a stationary sitting somewhere. So the force is there, but the force is not doing any work. Okay. Shall I move ahead? Is there anybody who want to ask anything within the solution of this problem? Okay. Okay, so let's have another problem. A fan that consumes 20 watt of electric power when operating is claimed to discharge air from a ventilated room at a rate of 1 kg per second at a discharge velocity of 8 meters per second. Determine if this claim is reasonable. So let's say we have a manufacturer of the fan, and the manufacturer of the fan is saying that this fan is going to consume 20 watt, okay, and if the ventilation is about 1 kg per second, if so it can basically uh, provide a discharge of air at a velocity of 8 meter per second. Now, using 20 watts producing velocity of 8 meter per second, is it really possible? Is it thermodynamically true? We need to see if this claim is correct or not. Okay, so this is the question. Before moving towards the solution, always the first step is to understand the question or not. We as an engineer right now needs to find out if the manufacturer of the fan's claim is correct or not. He's claiming that this fan is going to consume 20 watt and is going to produce discharge air at a velocity of 8 meter per second. We need to know that is this claim correct? Can 20 watt uh, able to produce a velocity of air discharge at 8 meter per second? So before moving towards the solution of the problem, first of all, do you understand the problem statement?
Yes, sir.
Okay. Now let's see the solution here. First of all, one thing is pretty assumed here right now, that before, if the fan was not there, if the fan is not working, so the air is stationary, or you can say that it is still air. Okay, so let's say the fan is in the room or where you have a still air, it's not moving air. Okay, so the all the velocity, so when we say that the fan is adding velocity to the air, means fan is adding kinetic energy to the air. So all of the kinetic energy added to the air is because of the motion of the fan. So that means, suppose if the fan is working like 100% efficient, like all of the energy you are supplying to the fan, this fan is basically supplying all of that energy to produce the kinetic energy in the air. Then we need to just see that using this energy, how much kinetic energy can be produced, or if we have this much kinetic energy, what is the energy needed to produce this much kinetic energy? Okay, so this is the thing that we need to figure out. Okay, so there are two ways of solving this problem. Okay, so here basically what we have, work electrical in, this electrical work is being used to produce kinetic energy. The first law of thermodynamics here is stating this thing. Okay, we don't have any change in potential energy. We are not talking any change about any change in the internal energy. Okay, what we are saying is that whatever the work in, okay, and also E mass in, E mass out in this case will be equal. Okay, because the amount of air which is going to enter into the fan will be the same amount of air which is going to go out of the fan. So E mass in, E mass out is also, they are equal, so they're going to cancel out each other. Okay, we are not saying that any heat is being added to the air. Okay, so Q is also 0. We have just work in, which will be equals to the change in the kinetic energy. This is what we have now. Work in will be equals to the change in kinetic energy. Okay, and initial kinetic energy was 0, so whatever the final kinetic energy, that should be the work in. So our first law of thermodynamics actually ends up into this equation. Okay, and from this equation we are going to verify. Okay, now what the manufacturer of the fan is claiming is that the fan is going to utilize 20 watts. So let's put 20 watts here and see that if we know what is the discharge, okay, what is the maximum velocity that could be generated out. Okay, so if we put the mass flow rate discharge of the air, and we provide work electricity in as 20 watts, okay, then what we find out is that the maximum velocity, let's say there are no losses in the system, then the maximum velocity of air that could be generated is about 6.3 meter per second. And the manufacturer of the fan is claiming that 20 watts, by taking 20 watts, this fan can generate 8 meter per second. So that means the claim is false. Do you understand here?
Yes, sir.
Okay. You can do it other way around as well. Here what they did is that they took in order to verify, we put work electric in, and we can find out that what is the velocity, maximum velocity that could be generated. We can do it other way around. Let's say if we say that the work velocity out is 8 meter per second, so we can put 8 here, and we can find out that what would be the minimum amount of electricity needed to produce 8 meter per second of the discharge air. Okay, and we can find out it when you do this, you will find out it will be more than 20. So since it will be more than 20, so that means the claim of the manufacturer is wrong. So thermodynamically, we have just analyzed the claim that 20 watt can produce 8 meter per second, if it is correct or wrong. This was the solution of the problem. Is it clear? Is there anything within the solution which is not clear? Okay. Then we have another example here. There are two examples here. In fact, some more problems. These are the ones which you can say you can take it as exercise. Simple problems. Just you have to apply the first law of thermodynamics and make the solution. And with this, our chapter number 2 is finished. Okay. You have some practice problems. I have already provided you the solution of the practice problems, just so that you can practice yourself. You can see different variations of the problems. Okay. So with this, our chapter number 2 is finished. Is there anything within the solution of or within this chapter, theoretical concept, numerical solution, anything which is not clear, please ask. Okay, now let me discuss about, I have uploaded a few things yesterday night over the Google Classroom. Okay. First of all, I have provided the thermodynamic tables. Thermodynamic tables is there in the book as well, in the textbook. It is just directly taken from the textbook. Okay, but you need to have thermodynamics tables with you every time, because you need to go through the thermodynamic tables and get the values from it. So you're going to use it a lot. So it's better to have a separate copy of the thermodynamic tables with you. So it's provided to you. It's there in the textbook as well as separately provided to you. Okay, then I added the reference books. The reference books is the same book, but the 8th edition. Remember, the textbook we are using is the 5th edition one. Okay, and then you have 2 other reference books. Okay, of different authors. They are also being added. Okay, I added assignment number 2 as well, just so that you know. This is again the assignment. You have to do it on EES. Okay, and after that, I added the practice problems, okay, for all the chapters that you're going to go through them. Okay, the practice problems are specifically selected problems which are easily solvable by going through my lectures. Okay, so if you have attended the lectures properly, if you have understood the material, you can actually go through the practice problems and you can solve these problems easily. And that's it. Okay, now about the assignment. First of all, did you guys go through the playlist? Okay, it's okay. You don't need to actually, even in the beginning. The initial 6 videos which I have placed are from different authors, and if you just go through those initial 6 videos, that videos would be enough to solve the assignment number 1 in reality. Okay, so later on, all other videos are step by step for each and specific case of EES, each and specific parameter of EES, studying that in a bit more detail. So if you just watch the first 6 videos, that would be enough to solve the first assignment, I guess so. But obviously, since you're talking about a software, so software needs that you need to spend a little time practicing on it. I mean, the more the more you are fluent in working over the software, the more it's easy for you to work on it. Okay, so initially you will find a bit difficult because you're just studying the interface. You're just studying how the software reacts, how everything is there. But in reality, in this software, there's nothing much into it. It's just you need to substitute, you need to write the equations, provide the inputs, okay, and provide the input, write the equations, and that's it. The equations are going to solve. In fact, this software has the built-in capability to look at itself the order of the equations. You don't need to specify the order of the equations as well. Also, you don't need to specify what should be at the right hand side of the equation, what should be at the left hand side of the equation. The only thing that it sees is the number of variables is equals to the number of equations, and this is the basic fundamental law of the mathematics that it can solve.
Sir, I have a question related to the software.
Yes, please.
Sir, when I was watching the videos that you told, so
Mhm.
I was just replicating all the equations into the software, but
Mhm.
sometimes the software is not responding or it crashes, and the answers are not same. The I changed the units also, but it's
Mhm.
very haphazard and it's not very precise answers.
Haphazard in in what sense? You're not getting the same answers.
Yes, sir, not same answers. And if we talk about the graphs and the tables, so it is not generating tables after one attempt.
Maybe you have made some mistake in writing the equation. Okay, can you do one thing? When you make the ES file, which you are trying to solve the problem or do some exercise on it, okay, just save that ES file and send it to me, okay, on email,
Okay, sir.
let's say, okay, and I will check what you have done, and then I will respond to you that where you are doing the mistake, okay. And this is one thing. The second thing is that you need to spend a little time on this so that you will understand it much better, okay. And let's say if you have watched the first 6 or 7 videos and you start working over something and you find difficulty in writing the equations or doing things, okay, then in that case we can have a specific help session where majority of the students are okay with any specific time any day, no problem, okay. And if that time and day is also okay with me, then I can be available on the same Google meeting link, okay. And we can have a specific help session where we can discuss what are your issues in understanding the software. The software itself, look, the software is not compulsory for this course, but we are in an age where everything is being software is a specific tool which is being utilized in each and every field. So since this is being used everywhere in the world, so I think that our students should also be equipped with the knowledge of this software, okay. And so that's why I have added the assignments to be done over the software. It's not really difficult. You need to spend a little time and inshallah you'll be able to do it. Okay, now regarding your question that the software is crashing, okay, sometimes it crashes, okay. There are two reasons. The first reason is that this is not the licensed version which I have provided you, okay. The licensed version is a bit expensive, and this is something that could be purchased by the university. If the university do not have this software, then obviously I cannot provide you the licensed version. So licensed version for sure never crashes, but this is not a licensed version. This is only, I found it over the internet and it works fine on my computer when I try it many times, okay. So the software which I have provided you, this version is good enough for you to understand the software to whatever the level I want you to understand. It will just give you just the beginning, okay. The other thing is that this software uh, is being updated every year, okay. So the company, okay, they are adding more and more uh, options into the software, as it's being updated. So sometimes you might see something in the video and you will not that find that option in the software that I have provided you, because the software which I have provided you is an old version. Okay, but anyways, the new things, the new options are not necessary. Okay, the things which I want you to do, the simple problems which I want you to solve, those problems does not need the advanced options. Okay, so you just need to write the equations and then solve them by place the units, solve them, that's it, get the answer. And then for whichever the parameter you need to do the parametric study, you need to comment or put that variable in parentheses, and then generate a parametric table for the parametric study. And once you have the parametric table, you can draw the plot easily. Okay, so I want you to go through the software tutorials, okay, and then try to do them over the software which I have provided you. In case if you still have difficulty, then no problem, we can have a help session where we can discuss the software. Okay.
Excuse me, sir.
Yes.
Sir, does this software works with MacBook?
I have no idea. Did you try it?
I tried, but it was not installing.
No, the installation is not needed. You see, this software, when you open the software, okay, let me just show you. For example, if I can stop presenting this and then present your entire screen. Okay. Okay. So can you guys see my screen?
Yes, sir.
Okay. So what I do is that, look, if I go here, I have this EES. Okay. This is the EES which I have provided you. Once you extract it, you're going to have all these files. Okay, I have not installed it. It's just I extract it. This thing that I have provided you, I provide you EES32, this one. Okay, WinRAR archive. Okay, and if you just extract it, it's going to come up with like this folder. Okay, I open it. I did not install it at all. Okay, now there is an application file. I just run the application file. Okay. You see, the software was basically, this is the 2013 version. We are right now in 2021, so it's a quite old version right now, which I have provided you. But the software is open, right? So all you just need to do is whatever you need to write the equation. Let's say x equals to 1. I'm just giving an example. Okay, y equals to 2, and then z equals to x plus y. Sorry, z equals to x plus y. It's going to say 3 equations, 3 variables, solve, solution is done. Okay, when you need to generate the parametric tables, okay, so let's say you generate parametric tables, okay, x against z. Okay, so let's say I want to change different x values. So let's say I want to change for x value from 2 to 10. Okay, so for different values of 2 to 10, okay, I can solve this because I put this in parentheses. So now it's going to take the values of x from the table and it's going to solve these equations multiple times. So I have different values of z. Let's say if I need to plot it, so I need to plot xy plot. On x-axis I need the x value, on y-axis I need the z value. Just plot it. Can you see these things on the screen? It's very simple. There is nothing to it. Just need to put the equation, okay? And right now I didn't place the units because I just placed x, y, z. I didn't. It was not necessary to place any unit right now. Just need to explain you that how this works. Okay. So is this thing clear? Can you see this on the screen?
Yes.
sir. जी
Okay.
सर.
So the software is very easy software. It's not like a difficult, complicated software where you need to do a lot of programming and things like that. Okay, there are options of programming, but those I don't want you to do it right now. You don't need to do it. If suppose if somebody among you wants to do these things, you can do them in future. You can study them. Okay, the only tutorial videos which I have provided you are the ones where you understand the operation of basic operation of the software, and only the basic operation is needed to solve the assignment problems. Okay, like for example, if I want to write the first law of thermodynamics here, we studied the first law of thermodynamics. Okay, Q minus W plus E underscore mass underscore in minus E underscore mass underscore out is equals to delta delta U plus delta kinetic energy plus delta potential energy. Okay. Okay, so if I want to see it in the formatted equation window, see here, Q minus W plus E mass in minus E mass out equals to delta U plus delta kinetic energy plus delta potential energy. Okay, now I can write another equation. Q is basically what? It's Q underscore in minus Q underscore out. That's it. That's another equation I have written. So do you see this thing? It's very simple. You just need to write the equations, and then you're going to put the input values. If the number of equations equals to number of variables, it's going to solve it. As simple as that. Now tell me, is it complicated?
No, sir.
It's not complicated. The only thing is that, sometimes the first time when I had to use this, I'm not saying that you guys are at fault, but sometimes we are afraid of it. So the first time when I had to use this, I was also afraid. I thought that, oh, I don't know, it's so difficult, it's so complicated, I don't know. But it's not complicated. As you go through it, you're going to realize it's very easy. And I'm sure if you learn the software, it's going to help you in other courses as well, and maybe in your projects. Okay, so I'm sure it's going to be very helpful to you on that stages. Okay, and you see here, whatever I did the software crash? It did not crash. Okay, but still there is a possibility. I'm not saying that you're saying wrong. Sometimes the software also crashes, no problem. If it crashes, all the time keep saving it. Okay, and whenever you write the equations window, also copy these equations and put them into the notepad and save it as well. Suppose if your file crashes, you have your equations in the notepad. You can just copy from the notepad and again open the EES file and then put the equations there, no problem. Okay, so that your effort is not wasted. Is it clear?
Yes, sir.
Okay. Anything anybody want to ask? Okay, don't be shy. Okay, your questions are valid. They're legit. Okay, and I should answer them. So if you have anything you need to ask, you can ask. Look, the objective is not to put you in trouble. The objective is to make you learn a software which might be useful to you in future as well, and to compete you with the world. When the world is learning the software while learning this course, why can't you guys do this? In fact, you guys can do it better than the rest of the world. So if you have anything to ask, please ask. Don't be shy. Don't hesitate. Anything anybody want to ask?
No, sir.
Okay, good. So now chapter 2 is finished, and I'm going to start chapter number 3 after a break of 5 minutes. Is it okay?
Okay, sir.
Okay. Okay, just a minute. Let me first take the attendance right now. I did not take the attendance. Okay, so okay, can you guys do one thing? That in the chat box, just write present. So I will have your attendance directly available. I will put it into the Excel sheet later. Okay, so in the chat box, put present, write present. Okay, so I will have your attendance against your name. Okay, we're going to start back after 5 minutes. Let's have a break of 5 minutes, then we're going to start. Okay, students, can you see the screen for chapter number 3? Slides for chapter number 3.
Yes, sir.
Okay. So here in this chapter, right now, we're going to take a pause from the first law of thermodynamics. Okay, we are going to connect the first law of thermodynamics and apply it for different kind of systems in chapter number 4 and 5. Right now, what we are going to do is we are going to study uh, thermodynamic property tables. We have thermodynamic property tables at the end of the book, and they are also provided as a separate file to you within the folder of textbook in the Google class material. Okay, so we need to study that. Okay, and for that we need to study that what are pure substances, what are the phases of pure substances. Okay, what is the phase change process? About we're going to study about the property diagrams, property tables. We're going to study the ideal gas equation, and then we're going to talk about the compressibility factor. So this chapter itself is a very fundamental chapter and a very important chapter for the rest of the book and for the rest of the course. So these are some of lesson objectives. You can go through them yourself. Okay, so talk about pure substances, a substance that has a fixed chemical composition throughout. So we talk about a pure substance. It is a substance that has a fixed chemical composition. Okay, for example, nitrogen here, tank of nitrogen, tank of air, vapor, liquid. Okay, air is basically air is an exception. So air is a mixture of several gases, but it is still considered to be a pure substance. Okay, so for all other substances, the chemical composition should be same, but for the case of air, it's not just a single substance, it's a combination of multiple gases, but we will consider air itself as a pure substance. Okay, so this is just an exception. Otherwise, pure substance is something which has the same chemical composition. Okay, when we talk about the phases of a pure substance, so we have 3 fundamental phases of any pure substance. So a pure substance might be solid, in the solid phase, it might be liquid, might be gas. What is the difference between a solid, liquid, and gas? It's something you have studied previously in physics as well as in chemistry, so I don't think so that there is any need to go through the definition and the differences between these phases of a pure substance. Okay. Now let's talk about the phase change process. Okay. So this is a very important slide, and actually something related to it. I have also placed a small video related to it. Okay, the video I found it on YouTube, but explaining those phases in a much better way in that video, and you can go through that video later on. It's there already in the Google Classroom. So let us try to analyze the phase change process. Now let us say that I have a container, and this container, let's say I have a container, and inside the container I have liquid water. Okay, inside the container I have liquid water at atmospheric pressure and 20 degrees centigrade. Okay, at the top of the container I place a piston. This piston is movable, it can move up and down. Okay, the object of placing the piston is that it becomes a closed system. So water cannot go out, or anything from out cannot come in. Now, what I do is that I put a heater at the bottom of the container, okay, and I heat it. Okay, when I'm going to heat it, what's going to happen is that the temperature of the water is going to rise because of the heating. Okay, so the temperature of the water is going to rise because of the heating, and so like from 20 it will become 21, 22, 23, so it's going to continue to rise. Okay, so this is a specific state. This is a specific state of water where when I heat it, the water temperature will rise, but its phase would remain liquid. So whenever you have a specific phase of any substance such that it is in a liquid state, and if you heat it, it's not going to vaporize. It's not about to vaporize. Okay, so that is specific phase of liquid is known as compressed liquid. So this is a state known as compressed liquid. I'm going to go step by step. This slide, I'm going to spend some time on this because this slide will be the fundamental for your understanding. Okay, so I'm going to ask you step by step, do you understand this phase or not, or everything? Okay, so state one is compressed liquid. What is compressed liquid? You have a liquid. If you heat it, its temperature will rise, but it will still remain liquid. So this state is known as compressed liquid. Okay, or we have another name for it. We call it subcooled liquid. So these are the two names for the same thing. Okay. State one, compressed liquid or subcooled liquid means it is in a liquid state, and if you heat it, its temperature will rise, but it will still remain liquid. Do you understand state one or not?
Yes, sir.
Okay. Now, what will happen? Let's say we keep on heating. We keep on heating, its temperature will keep on rising from 20 to 30, 30 to 40, 40 to 50, 60, 70, 80, 90. Let's say it becomes 100 degree. Still water. Now the water is at 100 degree, but it is still water, still liquid. Okay. Now what's going to happen is that, let's say if I heat it a little more, then what will happen? Temperature would remain same, but some gases, some bubbles are going to appear. That means part of the liquid will start to vaporize. So if I have a liquid, it is still liquid. If I have a liquid at a state that if I heat it slightly more, some of the liquid will convert to vapor. This state is known as saturated liquid. We need to understand the difference between saturated liquid and compressed liquid. Both are liquids, but when you heat the compressed liquid, it will still remain liquid. But when you heat saturated liquid, it will start converting into vapor. So do you understand state two? Saturated liquid. I need a yes or no. If you don't understand, please say no, you do not understand.
Understood.
Yes, sir, clear.
Okay, let's move towards, okay, now you heat it more and some vapors start to generate. Okay, so now what will happen? Obviously the vapors start to generate, the piston is going to move up as the vapors are generating. So now at the top side we have the vapors, at the bottom side we have the liquid, but the temperature still remains 100 degree. So you keep on heating, now you will have vapor and liquid both present at the same time. If we have this situation, if that the vapor and liquid are both present at the same time, then this kind of a state is known as saturated liquid vapor mixture. Okay, so when you heat it, the liquid content is going to reduce, vapor content is going to increase. When you cool it, vapor content is going to reduce, liquid content is going to increase. So liquid and vapor content is going to vary if you heat it or cool it, but both will be available at the same time. Both will be available at the same time. Okay, liquid will be available as well as vapor will be available. Both will be available at the same time, whatever be the quantity. Okay, so this state is known as saturated liquid vapor mixture. Do you understand this is state 3?
Yes, sir.
Yes, sir.
Okay, okay. Now let's say that you keep on heating, liquid content is going to reduce, vapor content is going to increase. A time will reach when even the last drop of liquid has been converted into vapor. A time will reach that even the last drop of liquid has been converted into vapor. So this state is known as saturated vapor. But remember, it has just converted, all the liquid has been converted into vapor. So suppose if you remove even a small amount of heat from here right now, then some of the vapor will condense to liquid. So the condition where there is no liquid here, but if you cool it slightly, then some of the liquid will appear. Some of the vapor will be condensed to liquid. So this state is known as saturated vapor. So there is no liquid in it right now, but it is about to condense. Just you cool it slightly and some of the liquid is going to appear. This state is known as state 4 or the saturated vapor state. Do you understand this state? I need response. If you don't understand, tell me. I will explain you again.
Yes, sir. Understood.
Okay. Okay. Now what happened is that still it was 100 degree. It was 100 degree when it started to, when it was about to boil, and then it started boiling, and then after that all of the liquid has been converted into vapor. It's still 100. So it was 100, 100, 100. All three stages, state 2, state 3, state 4,
सर
all 100.
आप
Yes.
अटेंडेंस एंड में मार्क करेंगे, अभी आपने मार्क कर दिया जो हम लोगों ने कमेंट किया है।
बस जो आपने कर दिया वो मैंने मार्क कर दिया। ठीक है।
सर मैंने थोड़ा सा 2 मिनट लेट किया था, 12:13 पे किया था।
It's okay, no problem.
थैंक यू सो मच सर।
Yeah. Okay. So state 2, state 3, state 4, all the three states, we have temperature 100 degrees centigrade. Okay, so that was saturated liquid. Then we have saturated liquid vapor mixture. And then let's say all has been converted into vapor, but it is about to condense. Okay, so this is saturated vapor. Now let's say if you heat it further, what will happen is that now the temperature is going to rise. So till here the temperature was constant, but now the temperature is going to rise. So it's going to move from 100 to 110, 20, 30, 40 is going to continue. Let's say you reach to 300 degrees centigrade. So here we have all vapor, okay? But if you cool it slightly, its temperature will drop, but it will not condense. This state is known as superheated vapor. This state is known as superheated vapor, not about to condense. Okay, and this is state 5. Do you understand these 5 states or not?
Yes, sir.
So I'm going to summarize it. Initially, it was liquid, but when you heat it, it will still remain liquid, but its temperature is going to rise. This is known as compressed liquid or subcooled liquid. Then then a state comes when it is liquid, but if you heat it slightly, it will start vaporizing. And this is known as saturated liquid because it is still liquid. Then a state comes where you have liquid and vapor both present at the same time. This is known as saturated liquid vapor mixture. Then a state comes when all the liquid, the last drop of liquid has been converted into vapor. However, if you cool it slightly, then some of the vapor will condense back to liquid. This is known as saturated vapor. And then if you further heat it, now it is superheated vapor. That means it is all vapor, and if you slightly cool it, it will not condense. The temperature of the vapor will go down, but it will not condense. This is known as superheated vapor. So you have 5 different states of any pure substance. These 5 states are what? Compressed liquid or subcooled liquid, saturated liquid vapor mixture, saturated vapor, superheated vapor. These 5 states are fundamental to understand the thermodynamic property tables. Do you understand these 5 states or not? Is there any state, any point, anything throughout in the explanation which I have given you which is not clear to you? Please ask.
Sir, can you repeat the state 5?
State 5. State 5 is what? You have vapor, it's heated, and if you cool it slightly, the temperature of the vapor will go down, but it will not condense. It will not condense to liquid. The difference between state 5 and state 4 is that both are vapors, but in state 4, if you slightly cool it, part of the vapor will condense to liquid. Okay, but in case of the superheated vapor, if you cool it slightly, its temperature will drop, but vapor will not condense into liquid. Is it clear?
Okay, sir.
Sir, why will it not condense?
Because for condensation, it has to be at a point that now phase change can occur. Okay, when you have very superheated vapor, then its temperature will keep on dropping until it reaches a specific temperature that now at that temperature, condensation can occur. Remember, boiling and condensation occurs at a specific temperature. You have one specific temperature at which boiling and condensation occur. Remember, boiling and condensation are two opposite phenomena. Okay, boiling means converting liquid to vapor, and condensation means converting vapor to liquid. Okay, and they both occur at a specific temperature. Like for example, for water, that temperature is 100 degree. So if you have water at 100 degree, you can have liquid converted into vapor, or you can have vapor converted into liquid. You can have boiling, you can have condensation, but at 100 degree. Higher than that, you will not have condensation. Lower than that, you will not have boiling.
Okay, sir.
You get the idea?
Yes, sir.
So these are the 5 states, very important. Just memorize the names. Names are very important, okay? And these definitions, okay? You can see compressed liquid, not about to vaporize. It's liquid, not about to vaporize. Saturated liquid, about to vaporize. Saturated liquid vapor mixture, liquid and vapor coexist in equilibrium, means both liquid and vapor will be present. And yeah, if you heat it up, vapor content will increase, liquid content will decrease. If you cool it, liquid content will increase, vapor content will decrease, but both will be there at the same time. And then saturated vapor, it's all vapor, but it is about to condense. About to condense means if you cool it slightly, some of the vapor will be converted into liquid because it is at 100 degree. And this is superheated vapor. Superheated vapor means it has a lot of energy even after becoming vapor. Okay, so if you cool it a little, its temperature will drop, but it will not condense. Okay, so 5 states, very important. And memorize the names and memorize the definitions. Okay, it will be automatically in your memory because you're going to use it a lot, and you need to have a good understanding of it to study the thermodynamic tables. Okay, now let's say if I plot it on a PV diagram. Okay, so let's say this is a PV diagram. Sorry, TV diagram. Okay, TV diagram means temperature on y-axis and volume on x-axis. So when it is from state 1 to state 2, when I'm heating from state 1 to state 2, let's say from 20 degree to 100 degree, what will happen? The volume of the liquid increases. It makes sense, right? Because when you heat the liquid will expand. So the volume of the liquid will increase. Okay, so in the compressed liquid region, the volume of the liquid increases and the temperature increases. Okay, so this is compressed liquid. Then at state point 2, now it is saturated liquid, that if it is at 100 degree and it is saturated liquid, that if you heat it slightly more, then the heat is not going to raise the temperature, rather the heat will be used to change the phase from liquid to vapor. Okay, so when the phase is being changing from liquid to vapor, you know that vapor occupies a lot of volume, so the volume will be significantly increasing. You see here the increase in volume is significant. Okay, so it will be increase in volume will be high. but the temperature would remain constant, so it will be a horizontal line. So state point 3 is saturated liquid vapor mixture region. Okay, state point 3 is saturated vapor liquid mixture. State point 2 is saturated liquid. Okay, and then the vapor content is going to increase, liquid content going to decrease. A time will come that all of the liquid has been, last drop of liquid has also been converted into vapor. So now we have all vapor at state point 4, but it is still 100 degree. You see here, this boiling process started from the liquid to the vapor. It's all at the same temperature. Okay, now what happened is that if you further heat it, then the gas, the vapor which is being generated now, this vapor is going to expand. Okay, and you remember the expansion in vapor is more than the expansion in liquid. So you'll find that for the case of liquid, the line is like very close to vertical, but for the case of vapor, it is more inclined. Okay, so you will have a change in the volume as well as the change in the temperature. So if you keep on heating it, then the temperature is going to rise. At the same time, the volume of the gas is going to increase. Okay, so this is a state point 5, which is superheated vapor. So we have compressed liquid, subcooled liquid at 1. At 2, it is saturated liquid. At 3, it is liquid vapor mixture. At 4, it is saturated vapor. At 5, it is superheated vapor. Okay, so these are the 5 states I have drawn on a temperature volume diagram. Okay, and throughout the pressure of the water remains same. So this is one pressure, atmospheric pressure. The whole pressure of the water remains same throughout. Okay, before moving forward, do you understand the Stevie diagram for different phases?
Sir, what will happen if we increase pressure at 5?
We'll talk about that. If we increase the pressure, what will happen? We're going to talk about that. But right now, for one specific pressure, how the temperature and volume is going to change, and what are the different phases of the water from liquid to vapor. Important point is that those 5 state points which we discussed in the last slide. Okay, do you understand these 5 state points on the TV diagram?
Yes, sir.
Yes, sir.
Is there anything, anybody, don't be shy in asking questions from me, okay? Don't worry about that. So if you have any question, feel free to ask. Okay, so this is the TV diagram right now for specific pressure. We talk about the one specific pressure. Okay, now what we realize is that the TV diagram is for one specific pressure. It follows a specific pattern. Okay, the pattern was like this, as I showed you, that initially it is like an inclined line, then you have a horizontal line, then you have another inclined line. Okay, so you have compressed liquid, you have, this is the saturation region. Saturation region starts from 2 to 4, where 2 is saturated liquid, 4 is saturated vapor, and 3 is a mixture of liquid and vapor. Okay, and then after that, from 4 to 5, you have the superheated vapor. So this is for one specific pressure. Now you do understand one thing from your basic understanding of the physics and chemistry that you have studied before, is that if you increase the pressure, the boiling temperature increases. Okay, if you increase the temperature, the boiling increase the pressure, the boiling temperature increases. So this is what happens inside the pressure cooker. Why do we use pressure cooker? Because sometimes we need to cook food more quickly. The only way of cooking food more quickly is that if we cook food at a higher temperature than the boiling temperature. Okay, so at a higher boiling temperature. So how can we produce a higher boiling temperature if we increase the pressure? So pressure cooker is a device where it is like partially closed system. So you make a partially closed system. Because of the closed system, the pressure inside increases, and when the pressure inside increases, the boiling temperature inside increases. So the cooking is done at a higher boiling temperature, and so cooking could be done quickly. This is what's happened inside the pressure cooker. Okay, so one thing is clear: if you increase the pressure, the boiling temperature is going to increase. Right now, if the pressure was 1 atmosphere, the boiling temperature was what? 100. If we increase the pressure, the boiling temperature will be higher than 100, let's say 110. So the same curve will be followed, but this curve will be like slightly shifted up, like this. Okay, same curve will be followed, but it will be slightly shifted up. On the same way, for example, if we lower the pressure, then the boiling will done at lower temperature. So let's say if you are at a very high altitude, let's say you are in Murray or at a very high altitude, then at very high altitude you will find that the boiling will be done at temperature lower than 100. So in that case, again, the same curve will be followed, but it will be the boiling temperature would be at a lower temperature. Okay, so it depends upon the pressure. You keep on increasing the pressure, like the curves, same pattern curves, but they will be shifted upward. Okay, so they will be shifted upward. So what we realize is that if we change the pressures, the curves following the same pattern, the curves are shifted up or down. If you increase the pressures, the curves are shifted up. At the same time, one another thing is realized is that the saturation region from state point 2 to 3 keeps on dropping, keeps on becoming smaller if you keep on increasing the pressure. The pressure from 0.1 megapascal to 1 megapascal to 8 megapascal to 15 megapascal, and this region keeps on becoming smaller. A time will come when the saturated liquid and saturated vapor point actually joins together. So there is no saturation liquid vapor mixture region, and that specific point is known as the critical point. So critical point is basically what? It is the point at which the saturated liquid and saturated vapor states are identical. This is a specific definition of critical point. That means what? Suppose if you have a tank full of liquid, if it is at a critical pressure, then once you heat it slightly, once it is at a saturation temperature, the whole tank of liquid is going to convert into vapor like magic. You will not see bubbles coming and then the process of converting liquid to vapor. The whole tank at the same time will convert into vapor from liquid like magic. Okay, so this is the critical point. And beyond critical point, the fluid is in a specific state that you can never judge whether it is in a liquid state or is it in a vapor state. So it looks like liquid and vapor both together. It's very hard to differentiate between them above critical point. So above critical point, there is no specific line which differentiates between liquid and the vapor state. So we have this kind of a curve, and this is known as basically the TV curve. Okay, now here, if you see here, there is a blue dome here, and this dome is basically what? If you join all the saturated liquid points and join all the saturated vapor points, so they're going to meet up at critical point. So this makes up a dome. Okay, this is the saturation region. So inside the dome we have all saturation region. We have liquid vapor mixture. The left side of the dome is basically saturated liquid line. The right side of the dome is the saturated vapor line for different pressures. Okay, and inside this dome we will have liquid vapor mixture all together. Okay, on this side you will have superheated region. Okay, all superheated vapor. This side you will have all compressed liquid region. So you have compressed liquid, you have superheated vapor, inside you have saturation region, and this line, the two lines that make up the dome are basically the saturated liquid line and the saturated vapor line. So there's a saturated vapor, there's a saturated liquid line. Okay, and the top point, the point where the saturated liquid and the saturated vapor line meet, is known as the critical point. Okay, so This is the PV diagram. This is the PV diagram. Okay, critical point for water is a specific point, and you have a specific pressure and a specific temperature for this. The critical point for water has a pressure of 22.09 megapascal and a temperature of 374.14 degrees centigrade. And the specific volume of water at that point will be 0.003155. Okay, so what I have shown you is the TV diagram for different pressures for water. Okay, and so based on the specific dome, you can actually judge that which is the superheated region, superheated vapor region, where is the compressed liquid region, and where is the saturated liquid vapor mixture region. Okay, so far, whatever the explanation I have given you, is this explanation clear or not?
Yes, sir. It's clear.
Anybody who has any question in the explanation which I have given, please ask.
No, sir.
Okay. Now you have to see one more thing, that for a specific pressure, there is a specific saturation temperature. Okay, like for example, when we talk about 0.1 megapascal, for this pressure, the saturation temperature is this, whatever it is. I don't know it is, how much, whatever it is, but it has a specific, so saturated liquid, saturated vapor, and the saturated liquid vapor mixture region all lies at that specific temperature. So for a specific pressure, you have a specific saturation temperature. So for example, for 1 megapascal, okay, so this is the specific temperature. This is the saturation temperature. For 8 megapascal, this is the saturation temperature. Okay, so for each one of it, okay, for each one of the pressure, there is one specific saturation temperature. Okay, and saturation temperature is the temperature where exists the saturated liquid state, where exists the saturated vapor state, or where exists the liquid vapor mixture. Okay, so there will be one temperature for each pressure. Okay, so that specific temperature is known as saturation temperature for that pressure. Or similarly, other way around as well. For every temperature, there will be a specific pressure. Okay, so for every temperature, there will be a specific saturation pressure, or for every pressure, there will be a specific saturation temperature. Both way around is possible. So for one temperature, there will be one pressure which will be saturated, which will be saturation.
Sir,
Yes.
so in the previous slide where you were
Mhm.
talking about a pressure cooker,
Mhm.
so you said when the pressure increases, the boiling temperature increases. So should
Yes.
the boiling temperature stay the same and पहुंच जल्दी जाना चाहिए उस टेम्परेचर तक?
No, the thing is that if you make it a closed system, then there is no, you need to understand the physics and the chemistry behind. Yeah, vapors are being generated, vapor need more space, but you are closing the system, so you are not allowing the vapor to escape. So what will
Yes.
happen? The
The
pressure
pressure
will increase, right? So when the pressure is going to increase, this is going to suppress the boiling process. There's a lot
this
of
is going
vapor.
to suppress the boiling process.
Yeah, it will not allow the water to boil easily. It will, more energy will be needed for the water molecules to convert into vapor, because there's no space for the vapors to go up. It's all filled with vapor upside. It's closed system. Are you getting the point?
No, sir. ऐसा नहीं होता कि when pressure increases, the temperature increases as well.
Yeah, this is what I'm saying you. When pressure increases, then the boiling temperature increases. Means the temperature at which the boiling can occur, that increases. Why? Because
Not the temperature of the system.
not the temperature of the system, but when the pressure increases, the boiling temperature increases. Temperature, pressure, they are independent of each other, irrespective of the saturation, only except for the saturation state. Okay, for the saturation state, temperature and pressure are codependent over each other. So for a specific pressure, you will have a specific saturation temperature, or for a specific saturation temperature, you will have a specific saturation pressure. Otherwise, they are independent properties. Okay, they don't depend over each other. The only thing is that if you increase the pressure, okay, it will make the liquid to it will make more hard for the liquid to convert into vapor, so the liquid will stay in the liquid state for a longer period, and so the temperature of the liquid would be higher at which the boiling is going to start.
So if we want to boil water, if we close the lid of यानी जिस भी चीज में boil कर रहे हैं, if we close the lid, so it will take longer to boil the water as
Yes,
compared to without the lid.
yes. So this is what happened. When I close the lid, I make it a closed system. I increase the pressure inside, and it will take me longer to boil the water. But when
That
the
is
boiling
because
is
it's
going
being
to, but when the boiling is going to occur, the boiling will be at a higher temperature.
okay.
It will take longer for water to boil, but the boiling will occur at a higher temperature rather than if we keep the lid open.
That's because vapors will find it difficult to form because of the increased pressure.
Exactly. Get the
Thank you,
idea?
sir.
Okay. Very good. Any other question? Anybody want to ask? It's good that if you understand the chemistry behind and the physics behind, then when you're solving the problems, when you're dealing with the thermodynamic cases, you're not just dealing with numbers, you are understanding the problem. That's good. So anybody have any question, please feel free to ask. Okay, so this thing is right now, I think, pretty clear that for every saturation temperature, there is one specific saturation pressure, and vice versa. For every saturation pressure, there is a one specific saturation temperature. So this is a specific temperature and pressure where the boiling or condensation takes place. Okay, so for 1 atmospheric pressure, water will boil at 100 degree. It will not be 101, it will not be 99, it will be 100 for 1 atmospheric pressure. But if you change the pressure, then the temperature at which the boiling or condensation occurs will also change. Okay, so the temperature at which a pure substance changes phase at a given pressure is the saturation temperature, or the pressure at which a pure substance changes phase at a given temperature is the saturation pressure. So temperature, for every temperature, you have a specific pressure. So you see here at 101.4, which is atmospheric pressure, 101.325 is the atmospheric pressure. The boiling point of temperature, the boiling point of water is 100 degree. But if you decrease the pressure, then the boiling point of water decreases. And if you increase the pressure, the boiling point of water increases. Okay, so for a specific pressure, you'll have a specific temperature at which the boiling can occur. Is this concept clear so far? If anybody have any question, you can ask. You see here, we can identify different regions. Okay, so you have saturated liquid line, you have saturated vapor line. The two lines where the two lines meet is the critical point. Okay, and then towards the left of the saturated liquid line, you have the compressed liquid region or the subcooled liquid region. Okay, towards the right of the saturated vapor line, you will have the superheated vapor region. But inside the dome, you will have saturated liquid vapor mixture region. This is a mixture, liquid and vapor both will be present. Okay, so this is basically the TV diagram. Okay, and so you'll have different pressure lines here. Okay, for constant pressure lines, we call these constant pressure lines. So because the pressure remains constant throughout these phases as the temperature and specific volume are changing. Is this diagram clear? If it is not clear, you can ask me that, okay, what point is not clear? Now I need response.
Yes, sir.
Okay, now you have to understand one thing. Okay, let me ask you one thing. Let's say if I have a gas, okay, and if I heat that gas, what will happen to the volume of the gas? Will the volume increase or decrease? I have a gas, and if I heat the gas, what will happen? The volume of the gas will increase or decrease?
It will increase.
It will increase. Okay. Now tell me, if I have a gas and I put pressure on the gas, if I have a gas and I put pressure on the gas, so will the volume increase or decrease?
Decrease.
Decrease. Now you
Decrease.
decrease. Now do you see something that if I increase the temperature, the volume increases, but if I increase the pressure, the volume decreases. Pressure and temperature both have an opposite reaction over the volume. Increasing the temperature increases the volume, increasing the pressure decreases the volume. Is this point clear? Pressure and temperature in nature has an opposite reaction over volume. They go like opposite ways. So if this is the point that the pressure and temperature behaves opposite to each other in terms of their reaction to the volume, okay, so the previous ones were the TV diagram. So in the TV diagram, the constant pressure lines were like going up. Here, if we draw the PV diagram, so the same, so the constant temperature lines would be like going down, because temperature and pressure have an opposite reaction to the volume. Okay, so if you increase the temperature, the volume will increase, but if you increase the pressure, the volume will decrease. Okay, so if you see here, this is a PV diagram. Here we have on y-axis pressure, and we have constant temperature lines. Previously we had on y-axis temperature, and you had constant pressure lines. These are very similar diagrams. The only difference is that in case of TV diagram, when you are increasing the temperature, the volume is increasing. But in case of PV diagram, when you're increasing the pressure, the volume is not increasing, the volume will decrease. Okay, so it's like the mirror image. Okay, or it's like tilted upside down. Okay, so here the lines were like this, going up. In case of PV diagram, the lines will be going down. These will be the constant temperature lines. Again, you will have a compressed liquid region, you will have saturated liquid vapor region, you will have superheated vapor region, you will have critical point, you will have saturated liquid line, you will have saturated vapor line. Okay, and then if you draw the constant temperature lines, so they will go like this, going down, because pressure and temperature have an opposite reaction to specific volume. However, specific volume respond opposite when it comes to temperature and pressure. Is this point clear? Okay.
Yes, sir.
Okay. So this was very fundamental diagram. This was the PV diagram is a very fundamental diagram. Okay. Similarly, TV diagram is a very fundamental diagram. These diagrams are very important to understand the thermodynamic tables. Okay, now let's talk about extending. Okay, we were talking about just liquid and vapor region, but we can extend the diagram to the solid or liquid region. And so right now what we were discussing was only this region. Okay. Sorry. Right now what we were discussing was only this region. So liquid vapor region, then we have this dome, you have superheated vapor, you have compressed liquid, but you can extend it. So if you further cool, then the liquid will start converting into solid, and then you will have solid here. Okay, then there is a triple line as well. Okay, where all the three states can coexist together, and then there's a possibility that you can convert, you have solid and vapor together. Okay, so this is a PV diagram, which is an extended form of the PV diagram. for the case where you have all the three phases together, solid, liquids, and gases. Okay, this is not important for us. For us, the major or important part was only these diagrams. Okay, where you have the liquid and the vapor region. So we are not going to deal with the solids too much. In fact, we are not going to deal with the solids at all. Okay, but anyways, you need to have an understanding that how would the PV diagram look like if we have an extended version of it for solid, liquid, and gases. Okay, you need to understand as well that for the case of water, there is an abnormal behavior of water. Now, what is the abnormal behavior of water? What is the abnormal behavior of water? Anybody have any idea?
Sir, the normal behavior of water is that it turns into solid below 0 degrees Celsius, and it turns back into liquid like above 0 degrees Celsius.
No, the normal behavior is that for the case of all the fluids, when they are converting into solid, okay, so at that the process takes place as the heat is being taken out of these liquids, so they contract while converting into solid. But for the case of water, instead of contracting, it starts expanding after 4 degrees centigrade. So below 4 degrees centigrade, it starts expanding. That's the abnormal behavior. So for those liquids which exhibit a normal behavior, the PV diagram, the extended PV diagram would look like this. The anomaly occurs where during the process of sorry,
ये अनॉर्मल बिहेवियर दोबारा बता दें जो वाटर का होता है।
वाटर का नॉर्मल बिहेवियर ये होता है कि कोई भी लिक्विड अगर आप उसको कूल करेंगे तो वो कॉन्ट्रैक्ट होता है, वो कॉन्ट्रैक्ट होने लग जाता है। हीट करने पे एक्सपैंड होता है, कूल करने पे कॉन्ट्रैक्ट होता है। ओके, वाटर के केस में क्या होता है कि कॉन्ट्रैक्शन कंटिन्यू होती है टिल 4 डिग्री सेंटीग्रेड एंड आफ्टर दैट इंस्टेड ऑफ कॉन्ट्रैक्टिंग इट स्टार्ट्स एक्सपेंडिंग। ओके, सो दैट्स व्हाई जो आइस होती है उसके जो डेंसिटी है वो कंपैरेटिवली लेस देन वाटर होती है। दैट्स व्हाई आइस फ्लोट्स ऑन वाटर। So that's the abnormal behavior. Otherwise, for other liquids, ice will be less dense than the water. Okay, than the liquid. So, but for the case of water, ice is for other liquids, ice will be more or the solid form will be more dense. But for the case of liquid, for the case of water, ice is less dense. That's why ice floats on water. So ये जो normal behavior है ये occur होता है for water below 4 degrees centigrade. And this, yes.
Sir, apart from hydrogen bonding, is there any other reason why water exhibits such behavior?
In fact, no. It's basically the hydrogen bonding which is basically responsible for this kind of a behavior. But anyways, this is not the subject of this this is not the matter of this subject. So we are studying thermodynamics. This is basically a matter of chemistry. We're going more into details into that. So most probably it's basically because of the hydrogen bonding, which is mainly responsible for this thing. So you have, if you have a liquid which behaves anomally, so for those liquids, the PV diagram looks like this, as I've shown you. And if you have other liquids where there is no abnormal behavior, then the PV diagram looks like this. But the only difference is when liquid is being transformed into solid. Okay, so the abnormal behavior is appearing only in that region. Otherwise, for the rest of the PV diagram, it's exactly the same as any other fluid. Now, regarding this diagram, what is the thing that you should understand or memorize? You should be able to redraw these two diagrams. I can ask you to redraw these two diagrams. Okay. So you need to know that what are the regions where you have the liquid, solid, vapor. Okay. Where you have the triple line. Triple line is basically what? It is basically a specific point where the liquid, vapor, and the solid, all three can coexist in equilibrium. So for each and every substance, there is going to be a triple point. Okay. So like, for example, for each and every substance, there will be a specific critical point. So there will also be a specific triple point. This was the PV diagram. If you want to draw the PT diagram for the PT phase diagram, then it will look like this. So you'll have sublimation. Sublimation is basically what? Converting solid to vapor directly. Okay. So this thing sometimes happens that, for example, you have different kind of fragrances which are in the form of a candle or something. Okay. So here those solid material directly converts into vapor. Okay. So this is just an example of sublimation. So where the solid does not convert into liquid and then to vapor, or directly solid converts from solid to vapor. So substance convert from solid to vapor. This is sublimation. So you have a sublimation process, okay, then you have vaporization process between liquid and vapor, you have a melting process between liquid and solid, okay, but the melting process for the substances that expand on freezing, okay, like for example water, it will be this, and for the other substances that contract on freezing, so it will be like this. So this is again a PT diagram, not significant for our course, but you should know how to draw the diagram and what are the processes for different lines. Okay, then for the specific case of water, the triple point is 0.01 degree centigrade, and the triple point pressure is 0.6117 kilopascal. So this is a specific point. At triple point, the pressure and temperature, at triple point pressure and temperature, substance exists in three phases in equilibrium. All the three phases will be there at the same time at this specific point. Sublimation is passing from solid phase directly into the vapor phase. So you need to know these definitions. What is a triple point? What is sublimation? Okay. What is a critical point?
Sir, here we are keeping volume constant, right?
Here, yeah, we are keeping
Sir,
volume
in the
constant.
previous temperature was constant.
The previous temperature was constant. Constant temperature lines will be there.
Sir, for different temperature, there will be different critical point.
Yes, definitely.
Yes, sir. Thank you.
Okay, so PVT diagram is here. This is just for if you want to look at it. There's no significance here in this course right now. So you can go through this diagram. It's a 3D version of solid vapor for the solid, liquid, and vapor. If we draw three axes: pressure, volume, and temperature. So for water, it is like this. For other fluids, that is like this. So property tables, inshallah, we're going to start from the next class. So for today's class, I'm going to stop at this point here. If anybody want to ask anything, you can ask. Otherwise, today's class is finished. Anybody want to ask anything?
We can mail them to you.
Sorry? I couldn't hear you. What did you say?
Sir, during the week, we have any queries, we can mail you.
Yes, you can email me. No problem. Okay. Also, my WhatsApp number is also with you. If you want to contact me on my WhatsApp, you can contact me on that as well.
Sir, where is your WhatsApp number?
I have uploaded the course outline on the Google Classroom, and the course outline. Okay,
sir.
Whenever you contact me, please, if, for example, if you are contacting me on WhatsApp, please introduce yourself, who you are, okay?
Yes, sir.
So, anything else anybody want to ask?
No, sir, nothing.
No, sir.
Okay, thank you. Inshallah, meet you next
Sir?
week. Yes.
Sir?
Yes.
Sir, regarding my attendance, sir, so जब attendance हो रही थी, so I lost my network connection. Can you please mark me present?
Okay, can you write present in the chat box?
Yeah, sure thing, sir.
Okay.
Okay, sir. Allah Hafiz.
Okay, thank you.
So I have written and I have written my roll number along with it.
Okay, thanks, sir.
Thank you so much, sir.
Officer.
No.
सर
Yes.
सेम इशू मेरे साथ भी यही है कि मेरा भी जो है कनेक्शन लॉस हो गया था
Okay, no problem. Just
और
write
फिर
your return.
समरा का मेरे पास मैसेज आया कि उसकी जो है लाइट चली गई है तो वो लिख नहीं सकती तो उसका भी मैं लिख दूं
चलें,
इशू
कोई
जो है
बात नहीं, कोई बात नहीं, मैं उनका
ओके
लगा
थैंक
दूंगा,
यू
no
सर
problem. For me, attendance is not a big issue, okay? So just write present in the chat box. That's okay.
Okay, sir. Allah Hafiz.
Okay, Allah Hafiz.